Hey everyone, I am Miss Hu, your physics teacher. In this video, we'll be going through the general properties of waves where we will learn about the wave definition and features, transverse and longitudinal waves, as well as the wave equation. Now, this video will be covering the content that students need in order to answer the questions in their SPM physics and IGCSE physics examinations. There's always, of course, a lot more to know about this topic, so please feel free to do your own additional research, or you can watch my other videos about waves. Now, let's get started. First of all, we need to know what are waves. By now, you should already know that there are many different types of waves. You should be able to name at least 3 off the top of your head. Sound waves, light waves, radio waves, microwaves, even water waves. So all of these, of course, are waves. But what makes a wave a wave? Like, what does it mean when we actually say wave? So here's the definition of a wave. Wave is a traveling disturbance originating from an oscillating or vibrating source. Take water as an example. When a water wave travels on the surface, there is a disturbance because it's disturbing the calm level of the water. All waves will have an oscillating or vibrating source. Oscillation is when an object moves back and forth along a fixed path, like a pendulum. Vibration, very similar except that it's much quicker and around the same spot. So we use both terms oscillation and vibration because some objects oscillate but don't vibrate. For example, a pendulum doesn't vibrate, it oscillates. And then there are also some objects that vibrate but do not oscillate. For example, your phone vibrates but not oscillates. So what's actually happening inside a wave? A wave transfers energy but not matter. So you can think of waves simply as a way for energy to get from one point to another. So sound wave, for example, will be transferring sound energy. Light wave will be transferring light energy. Water waves are transferring kinetic energy. Now, in order to model the wave, normally we will use a slinky spring because it's much easier to be able to see what's happening with the wave particles. So we're going to be observing the slinky spring, which I'm going to shake to model the wave. So in this example, you can see that I'm shaking the spring on the left-hand side and my hand is mimicking an oscillating source. So that causes the entire spring to shake as well. So as you can see that there was a traveling disturbance from left to right. Let's watch that one more time. And you can see that energy is being transferred from left to right within the spring. Now, what it means when we say that a wave doesn't transfer matter is that the particles are not traveling along with the wave. If we were to observe the spring again one more time, you can see how the particles are pretty much shaking up and down. Energy is moving from left to right, but the spring particles are not moving along with the spring. Now, this is an important thing to note because when it comes to waves, a lot of students always think that the wave particle is moving along with the energy. For example, water. So when they see the water waves that are being created, they think the water particles are moving along with the wave. Actually, that's not what's happening. Water particles behave exactly like what we saw in the slinky spring model. The wave is moving from left to right, but the particles are pretty much staying where they are, hovering or oscillating around the same spot. And that's what's happening with water waves as well. Now, this is not the only way in which energy can be transferred in a wave. Another way is to oscillate this way. So as you can see, now we're pushing the spring forward and backward. My hand was still mimicking an oscillating source, so it's moving forward and back around the same path. Energy was still being transferred from left to right, but not matter. However, the difference is the direction in which the wave was oscillating. So what you need to know is that there are 2 types of waves. So the first type of wave that we modeled is called a transverse wave. Transverse waves are waves where the vibrations or oscillations of particles are perpendicular to the direction of travel. So what does this mean? Let's start first with the direction of travel. The direction of travel quite simply refers to the direction in which the energy is traveling along the wave. Some people call it the direction of wave motion, some say direction of wave propagation. As you can see from this video, the energy was traveling from left to right. Ignore the up and down movements. Generally, the energy started on the left, and then on the right, it was traveling from left to right. Now, if we were to observe the direction of the wave vibration or oscillation, you'll find that they are perpendicular to the direction of travel. To understand this, let's observe one point on the slinky spring. So you can see there's colors on the spring. Just zero in on one of the points. Let's say the green color point on this slinky spring. So keep your eyes on the green color point and let's observe how it moves. And you can see it's moving up and down. It's not traveling along with the wave. It's quite simply oscillating up and down. So when we talk about the direction of oscillation, we always have to compare the direction against a standard direction. We cannot say, oh, transverse waves, all transverse waves will always oscillate up and down. That's not true, because what if the wave was traveling this direction, like this? So you have a wave traveling up to down, or down to up, or diagonally. So you can't always say that, oh, the oscillation is up to down. We have to compare the direction of oscillation against the direction of travel. So whenever we give the general definition or general explanation of the transverse wave, you have to compare the direction of oscillation against the direction of travel. And as we have already observed earlier, we know that the wave particles are oscillating in a direction that is perpendicular to the direction of travel. And that's what this sentence means. And now for the second wave. The second wave is a longitudinal waves. Longitudinal waves are waves where the vibrations or oscillations of particles are parallel to the direction of travel. And as we can see in the video, the waves are also traveling from left to right. So the direction of travel is from left to right. The energy started on the left side and ended on the right side. And if we were to zero in on one of the coils, again the green part of the coil, let's watch that again, you can see that the green color part of the coil is moving back and forth, again oscillating around the same area. So that's why we say the direction of oscillation is parallel, because they are moving along that same line of the direction of travel. However, be very careful, students. You cannot say that the longitudinal waves are waves where the vibrations or oscillations of particles are the same as the direction of travel. You cannot say that. The reason is because it's not the same. The direction of travel is from left to right. If you say same, what you're saying is that the vibrations or oscillations are from left to right. But as we saw in the spring, the particles are not only moving from left to right, they're actually going backwards as well. So they're going forward, back, forward, back. So because of this constant change in direction, you cannot say that they're the same as the direction of travel. But we do know that they're traveling along the same line. So that's why we say they are parallel to the direction of travel. Now let's go into the features of a wave, where we'll need to know the measurable quantities about a wave. All of this information applies to both the transverse and longitudinal wave. No matter what kind of wave, whether transverse or longitudinal waves, all of them have the same measurable features. So what we're looking at on this slide are the features of a wave, or the measurable quantities of a wave. On the left hand side here is the list, and on the right side are the definitions of those measurable quantities. Let's look at each one in turn. Starting off with wavelength. Wavelength is normally represented by the symbol lambda, which is taken from the Greek alphabet. So that's why it doesn't look like any of the letters that you are familiar with. In brackets are the different units which we can use to measure wavelength. Because wavelength is a length, we can measure wavelength in meters, centimeters, or millimeters. The definition of a wavelength can be stated as the distance between two consecutive crests or troughs, or the distance between two consecutive compressions or rarefactions, or you can say the distance between two consecutive points of the same phase in a wave. Now, in case you're wondering what all of this means, we'll take a closer look at how this applies in the transverse and longitudinal waves in the next few slides. For now, you can think of wavelength as being something like the length of one wave. By the way, yes, wavelength is a proper term. It's not two words smushed together to become one random word. No, wavelength is a physical quantity in physics. And yes, you can think of it as length of one wave. So for example, if you were to take the pendulum as an example, you know how a pendulum is swinging between two extremes. So you start from one point all the way to the other and back. That's one full cycle. So if this was then seen in a wave, if you could measure the length of that one complete wave, that would be the wavelength of that wave. Next, period. It's normally represented with capital T, and the unit we normally measure it is in seconds. Period is the time taken for the wave to make one complete oscillation or vibration. The term period in physics always refers to the time to make one. So for example, the period of oscillation of a pendulum means the time taken for a pendulum to make one complete oscillation. Frequency is normally represented by the small letter f, and it's measured in hertz. Frequency is the number of complete oscillations or vibrations of a wave in 1 second. So for frequency, you can think of it as how frequently something occurs, how many waves there are in 1 second, how frequently this wave is oscillating in that 1 second. So we use 1 second because second is the SI unit of time. Amplitude is the maximum displacement of the particle from its position of equilibrium. Because amplitude is a type of length, it could be measured in meters, centimeters, or millimeters. Now we will take a closer look at all of this in the following slides in terms of the transverse and longitudinal wave. For now, let's just go through the relationship between period and frequency. Period and frequency are kind of the inverse of each other, because as you can see, period is the time taken to make one complete oscillation, but frequency is how many oscillations there are in that 1 second. So the relationship between the two is written this way. If f is the frequency and capital T is the period, you could calculate frequency as 1 divided by the period. So hertz is essentially equivalent to per second. Now, if you don't quite understand this relationship, one way to understand it is by looking at numbers, because sometimes using numbers just makes a whole lot more sense. So, for example, say the period of a wave is 10 seconds. So that means one wave takes 10 seconds to complete. If you look at how frequently that wave is occurring, then it's like, oh, definitely it's not even 1 in a second, because one wave takes 10 seconds to complete. So if we were to calculate the frequency, it would give us 0.1 hertz. That means about 1/10 of that wave is occurring every second. If this doesn't quite make sense, you can also look at it on the flip side. Say, what if the frequency of the wave was now 10 hertz? That means there's 10 of them in 1 second. So if there's 10 waves in 1 second, each wave would take only 1/10 of a second to complete. Now, from the formula f equals 1 over t, this also means that t is 1 over f. So when you calculate it, you get 1 over 10, giving you 0.1 seconds. That means that the period of a wave is 0.1 seconds. One wave takes 0.1 second to complete. So hopefully this helps you understand the relationship between period and frequency. It is important to know this because sometimes in a question, they may give you the value of the period of the wave, but you need to determine the frequency of the wave. So how you do that? You use this formula to calculate it. So now let's take a look at how these features can be obtained from the waves, starting first with the transverse wave. On this slide, we have a diagram here that represents the transverse wave. We have the hand that's oscillating the string up and down to create the transverse waves. Before we go into the features of a wave, let us first identify the different key phases of a wave. So the term phase here refers to the point of the cycle in the wave. We give names to the key points or the key phases of the wave, so that's easy for us to be able to identify the different parts of the wave. So as you can see in a transverse wave, it's very easy to identify. We've got the topmost points as well as the bottommost points. The topmost points of the wave is known as a crest. Sometimes it may be called a peak. It is more common to hear the word crest than peak though, but I've included this term here anyway because you might come across some books or notes which still use the term peak. Now the bottommost point on the transverse wave is known as the trough. It's like cough, but starts with a TR, trough. The term trough comes from the shape, which is a bit like a V shape, although not really V, it's a curved V. Now let's go into the features, starting first with wavelength. So wavelength is the distance between two consecutive crests or two consecutive troughs. So if you look at it, yeah, it makes sense, right? Because you start from one crest, and to make one complete wave, you need to go to the next crest. The term consecutive means one after the other. You cannot take from any two random crests. If you take between two, oh, that's already much longer than one wave. So remember, a wavelength is like the length of one wave. So you start on one point of the wave and you measure the length until the next point, the exact same phase. But when you measure the length, you don't measure along the wave, you measure across from one point direct to the next point. So which means that if we were to measure the wavelength, one way we could measure it is from crest to crest. So I'm going to draw from this crest over here so that the diagram doesn't get too cluttered. So starting from this point, we would go to the next crest, and the wavelength is measured this way, direct from crest to crest. I'm going to label it with the symbol lambda. Instead of measuring from crest, you could also measure from trough, because as long as you're measuring across the length of one wave, that would still give you the value of the wavelength. So let's start from this trough to the next trough, and that's the wavelength. Now you don't always have to start from crest only or trough only. You can actually start from any point on the wave as long as you end on the next point in the exact same phase. So for example, if you wanted to start from the middle of the wave, you could. But here's the thing. Just because you start from the middle doesn't mean you go to the next middle. For example, like here. Because if you look at it, from here to here, that's not one complete wave. Like for the pendulum, you'd oscillate, come back, and that's it. That's not one complete oscillation. For one complete oscillation, if you start here, you've got to go to both extremes before you come back to the middle. Likewise, for the wave, one complete wave has to go to both extremes before it comes back to the middle. So that's why you don't stop at the next middle. You have to stop at the next point in the same phase, which is over here. And then when you measure this, you can get the same value of the wavelength as with the other two values. I think this is not so accurate. Let me just fix that a little bit. To this point, that would be the wavelength. There we go. Now, if we have a diagram like this where we're measuring the wavelength, you cannot measure period from this diagram, because if you've taken your ruler to measure the wavelength, period has to be measured with a stopwatch. So you do not take period from this diagram. That's why you also cannot get frequency from this diagram, because frequency is dependent on the period. So let's skip period and frequency. Let's move on to amplitude. Now, amplitude is the maximum displacement of a particle from its position of equilibrium. So what does that mean? So imagine again, if we have the spring as the model of the transverse wave, if we don't shake the spring, this is the original position of the particles of the spring. When we apply energy, of course, we start creating a wave, and you'll find that the particles of the spring have been displaced from their original positions. That's what displacement means. The displacement refers to how far each particle on the wave has been moved from their original positions. So let's say now in this diagram, I'm drawing with dotted lines the original position of the string before the wave creates a disturbance through it. And it so happens that the original position is the same as the position of equilibrium, because position of equilibrium here refers to the equilibrium between the two extreme points. So that's in the middle. Now my line's a little bit off center, but let's just imagine it's straight, alright? So maximum displacement here refers to the biggest value of displacement of the particle from their original positions. And as you can see, this can be measured from the crest to the equilibrium position, or you could take it from the trough to the position of equilibrium. So I'm going to label the amplitudes here as A. So these are the two key phases of the transverse waves and how we can measure the wavelength and amplitude. Now let's take a look at the longitudinal wave. So in this diagram, the longitudinal wave is represented by the slinky spring. The hand here is mimicking the source of energy, so it's oscillating the spring parallel to the direction of travel. Now let's first look at the key phases of the longitudinal wave. As you can see, there's no high and lows, so there are no crests, no troughs. Longitudinal waves do not have crests and troughs. Instead, they have areas where the wave particles could be really close to each other, or they could be stretched out. So the key phases of the longitudinal wave are different from the transverse wave. In this case, they have a region of compression, which is where the particles are really close to one another. And the area that is stretched out is known as rarefaction. Now, to measure the wavelength, we know the wavelength is the distance between two consecutive compressions or two consecutive rarefactions. Having said that though, you cannot just randomly select any 2 points within a compression and say, oh, that's the wavelength. So for example, if you did this, say, oh, compression to compression, ta-da, this is the wavelength, that would already be wrong. Why? Remember what we learned in the previous slide. The wavelength must be measured between 2 points in the same phase. So although the compression is a region and rarefaction is a region, in order to measure the wavelength, you have to start from one point on the wave and find the next point in the exact same phase or same point in the cycle. So if you were starting from the beginning of a compression, let's take this point, you must find the next point which is exactly the same as this point in the next part. Remember, consecutive, you got to find the next point. So that would be, say, up to about here. This would be the wavelength. So if you were ever asked to mark the wavelength in your exam paper, you have to be very exact in the 2 points that you have selected to mark the wavelength. You can also do the same thing for rarefaction. Again, you must start from the same point and end in the next point of the exact same phase. Say, for example, if I were to start from the second coil of the rarefaction, you must then end in the second coil of the next rarefaction. This would be the wavelength. Similarly, we cannot obtain period and frequency from this diagram if we have already obtained the wavelength. Can we get amplitude? Well, actually you can measure amplitude from the longitudinal wave, but it is quite difficult because you first of all would need to get the original position, which means you need to have one diagram of this, and then you must get a second diagram where you see the maximum compression or maximum rarefaction and compare those two diagrams. Because it gets a little bit complicated, we don't do it for longitudinal waves. So good news, we only need to take amplitude from the transverse wave or from a wave graph. Now, before we go to the wave graphs, let's look at a couple of examples of how longitudinal waves could be presented visually. So besides representing the longitudinal waves with a slinky spring like this, sometimes we represent it with dots or lines. So why we use dots is because we know that sound wave is a longitudinal wave. So these dots are normally used to represent the air particles that will be carrying the sound energy. So how they can represent longitudinal wave, you can see that the dots are undergoing a series of compression and rarefaction. So you've got compression, rarefaction. So when you see this, you should be able to recognize, oh, these are actually air particles, and the air particles are going through a series of compression and rarefaction, which means that this is a longitudinal wave. Or another way, instead of drawing dots, they draw lines. So the lines are representing the position of the air particles this time. And again, you see the series of compression and rarefaction. In fact, this diagram also shows us how one wavelength is measured from the middle of one compression to the middle of the next compression. So now we'll take a look at a couple of wave graphs. In order to be able to obtain period and frequency, normally you need to have a wave graph. A wave graph is normally presented as a displacement-time graph. Now remember, the displacement here refers to how far the particle has moved from its original position. So you can think of the graph basically showing the movement of one particle. So let's say we look at the slinky spring again. Let's say we're observing this part of the spring, and over time we see, oh, it's moving up, down, up, down. So first of all, it starts from its original position. That's why displacement is 0. And as you start shaking it, it starts moving up and down. So basically, this graph is showing you the position of this particle as it's traveling over time. So its physical movement is only like this, but because you're running a timer, you can think of it as you put a piece of paper and then you're drawing it on that paper. So you find that because you're moving the paper, you get this graph. So this kind of shape is known as a sinusoidal shape. It's named after the sine graph shape because it looks exactly like a sine graph. So for those of you who want to know the name of the shape, it is a sinusoidal wave, named after the sine graph. Now, from a graph like this, we can now obtain the period because remember, period is a time for one complete oscillation. So looking at this graph, to find the period, you just need to find the time it takes for one complete cycle. So if you start from the middle, you go to two extremes until you find the next point on the same phase. So if you look at it like, oh, isn't determining the value of the period just the same way as how we determine the wavelength? Well, the method, yes, looking for one complete wave. So the length of one wave, you measure the length. Time also is the time for one wave. Yes, you look for one complete wave, so you could take from middle to this middle, or you can go from crest to crest or trough to trough. So yes, how you get the time period is the same as how you get it for a wavelength. The difference is that you can only get the period from a displacement time graph like this. So the period is measured from here to here. I'm going to label that as capital T for period. Now, from this graph, you can also measure the amplitude because amplitude is the maximum displacement of a wave particle from its position of equilibrium. So you could measure the amplitude from the time axis to the crest or to the trough. Now, this is the more common type of graph. You may occasionally get this kind of graph. It's a bit rarer, but it's also possible. This is a displacement-distance graph. So if you learn about motion, you'll be like, displacement and distance, aren't they like two different things on the same coin? Like one is scalar, one's vector, right? So when it comes to waves, this is what they mean. So again, displacement is how far the particle has moved from its original position. Distance, on the other hand, is how far the particle is from the wave source. So it's like if you have a spring like this, the distance is how far it is from the source. So if this is the source, we're shaking here, it's how far from this source. So you can think of the graph as a photo of the wave. So for example, if you're shaking this spring and you take a picture, snap, okay, you're seeing the displacement up and down and distance from the source. Now, if you have a graph like this, because it's a displacement distance graph, you cannot get period because this is not the time. Instead, you can get the wavelength because remember, a wavelength is a distance between two consecutive points of the same phase in the wave. Or you could measure it between two consecutive crests or two consecutive troughs. So you could measure wavelength from crest to crest, trough to trough, or for one complete cycle from middle to the next middle of one complete cycle. Now, similar to the previous graph, you can also measure the amplitude because amplitude is the maximum displacement. So you'd measure the amplitude from distance axis to the crest or to the trough. Now, one thing I'd like to highlight to you is about sound wave graphs. A lot of students tend to get very confused when it comes to sound waves. I'll just move my face out of the way first. Alright, so the thing about sound waves is that a lot of students think that sound waves are transverse waves because they tend to see that the graphs create the sinusoidal wave shape. One thing you must understand is that sound waves are longitudinal waves in terms of their physical behavior. That means that the sound waves undergo a series of compression and rarefaction when they're carrying sound, whether you're traveling through gas, liquid, or solid. However, for the graphs, they're sinusoidal shapes because that is the drawing pattern based on the movement of the particle. So they're not transverse waves. It just so happens that transverse waves and sound wave graphs have similar shapes. So how is it that a longitudinal wave is able to produce a sinusoidal shape? So now, let's imagine we have the slinky spring, and this is modeling the sound waves. If we could get a pen and stick it into the slinky spring, and get that pen to draw a line on a piece of paper underneath the slinky spring. So I want you to imagine now we've got a pen that we stick into the spring, and then we oscillate the slinky spring. And as the slinky spring moves, the pen is going to move with the slinky spring. And of course, it's going to go forward and back, forward and back. So if we were to place a piece of paper underneath that pen, of course the pen is going to draw one line. Now if we could move that paper, so imagine now we've got a piece of paper underneath that slinky spring, and we move that spring so that the pen moves along with it. Remember, it's doing this, it's going to end up drawing a wave that looks like this. So then when we get this graph, we turn it this way. That's how we're able to get the sinusoidal shape. So remember that when we look at this is just a graph that shows us how the particle is moving with time. It's not showing us how the sound wave is behaving in real life. So sound waves are longitudinal waves. They undergo compression and rarefaction. The graph is just what is drawn by the pen when we stick it into the wave and make the pen move together with the wave particle. So that's the difference. Remember, the wave graph shape is sinusoidal shape. Transverse waves and the graph shape have similar shapes, like a sine graph, like when you learn in math. A sine graph is just a result of calculating the sine value of the different angles. They're not waves either, but they have the same shape as a transverse wave. So remember, that's the shape, not the physical behavior of the wave. Now, one common point of confusion that a lot of students have is the comparison between amplitude and frequency. The thing is, amplitude and frequency are two very different things, and you'll explore more on this in sound waves. For now though, let's just have a closer look at the concepts of amplitude as well as frequency. When we want to relate amplitude and frequency with energy, here's how you can think of it. Amplitude represents the energy of a wave particle. So for example, if I shake this spring with less energy, the amplitude will be lower. If I shake it with more energy, there will be a larger amplitude. A lot of students also relate frequency with energy, and yes, there is a relationship, but frequency is related to the energy of the entire wave. Obviously, if there's greater frequency, there's overall greater energy. If the frequency is lower, then yes, the overall energy will be lower. So amplitude and frequency are related to energy, but in very different ways. One more time, amplitude is related to the energy of a wave particle. So when the wave particle has more energy, the amplitude will be greater. But if we're talking about energy of the entire wave as a whole, then that is related to frequency. So amplitude and frequency are independent of each other. Having a low amplitude doesn't guarantee that the frequency is low or high. And also the opposite is true. The frequency does not affect the amplitude in any way. So just because there's higher frequency doesn't mean that the wave will have a higher or lower amplitude. So if we look at these four waves, you can see how the amplitude and frequency are independent of each other. In this diagram, we have a wave that has low amplitude and low frequency. You can also have a wave with low amplitude but high frequency. This diagram shows us a wave with high amplitude, low frequency, while this final diagram shows us high amplitude with high frequency. So you can see how when the amplitude is much higher compared to this other wave, this means there's more energy. How come frequency is related to the energy of the entire wave? Well, if you compare these two waves, for example, for higher frequency waves, in the same amount of time, there are more waves compared to the lower frequency. The overall energy contained within that period of time obviously is much higher than those with lower frequencies. So in the next few slides, we're going to look at the comparisons between amplitude and frequency using the slinky spring as our model. First of all, I'm going to get my face out of the way. We're going to start off with low amplitude, low frequency. Now, low amplitude, high frequency. High amplitude, low frequency. As well as high amplitude and high frequency. Now for all of these, we were looking at a transverse wave as the example. You can also compare these with longitudinal waves. For example, low amplitude, low frequency, low amplitude, high frequency, high amplitude, low frequency, and high amplitude, high frequency. So now that we know about transverse and longitudinal waves, let's have a quick summary that compares the two. So transverse waves are waves where the vibrations or oscillations of the wave particles are perpendicular to the direction of travel, and as shown in this diagram, the key phases are the crest and the trough. You can measure the amplitude and wavelength as shown in this diagram. Longitudinal waves, on the other hand, are waves where the vibrations or oscillations of the wave particles are parallel to the direction of travel. The key phases are compression and rarefaction, and this is how you can measure the wavelength in a longitudinal wave. Now, another thing you need to know are what waves are transverse and longitudinal. So you need to be aware that all electromagnetic waves are transverse waves, and this includes light waves, radio waves, microwaves, infrared rays, X-rays, gamma rays. If you don't know what are electromagnetic waves, please watch my video on electromagnetic waves where we learn about the electromagnetic spectrum as well as the properties and applications of electromagnetic waves. So that's where you will learn about all the different waves in the spectrum. Also, you need to be aware that water waves are transverse waves as well as Seismic-S waves. Now, for longitudinal waves, all sound waves are longitudinal waves. This includes ultrasonic waves, which are in the range of frequencies that are higher than of human hearing, as well as subsonic, which are below that of human hearing. In addition, Seismic-P waves are also longitudinal waves. Now, this is all you need to know for in terms of the examples of transverse and longitudinal waves. For those of you who are taking SPM, you don't need to know about the Seismic-S and Seismic-P waves. If you're taking IGCSE, you do need to know all of this. Now let's talk a little bit about Seismic-S and Seismic-P. You might be wondering, what are Seismic-S and Seismic-P? The good news is that for IGCSE, the extent you need to know in terms of the seismic waves is that Seismic-S is transverse and Seismic-P is longitudinal. How you remember this is that S looks like the transverse wave, right? But sitting on its side. So you remember that way? Oh, S shape like transverse. So Seismic-S is transverse, which means that Seismic-P is longitudinal. Now, of course, if you're like, no, I need to know more about this, let's go a little bit more into what Seismic-S and Seismic-P are. So here's a little meme for you. Yeah, a seismometer basically is a device that detects seismic waves generated by earthquakes and nuclear explosions and draws out the wave graphs, similar to how I explained how sound waves generate those wave graphs. But if you prefer this kind of earthquake detection kit, you do you, man. So now let's go into the serious discussion. What really are seismic waves? So seismic waves are caused by the sudden movement of materials within the earth, such as slip along a fault during an earthquake. So volcanic eruptions, explosions, landslides, avalanches, and even rushing rivers can also cause seismic waves. So basically, seismic waves are caused by the movement of the earth. Seismic-P are primary waves. So P represents primary. Seismic-P waves are longitudinal waves, and because they're longitudinal, like so, they can travel through solids, liquids, and gases. Because of this physical behavior, they travel much faster than Seismic-S. Seismic-S, on the other hand, are secondary waves, so the S represents secondary. They're transverse waves, and because of that, they can travel through solids only. They're much slower than Seismic-P, but because of this behavior of the ground, they are far more destructive than Seismic-P. Understanding Seismic-P and Seismic-S is very useful because it helps us understand more about the structure of the Earth. Now, we don't need to go into this much detail because this is not coming out for our exams. So if you'd like to know more, please go ahead and do your own additional research to find out more about Seismic-P and Seismic-S and how scientists are able to use these to deduce the structure of the Earth. For now, let's move on. Now, when it comes to physics, we know there must be an equation somewhere. So this equation is very commonly known as the wave equation, and it's used to calculate wave speed. V is the wave speed, which can be measured in meters per second or centimeters per second. F is frequency, which is expressed in hertz or per second. Lambda is wavelength, which can be expressed as meters or centimeters. Now, of course, when using this formula, you must ensure that the unit you use, whether it's meters or centimeters, has to be homogeneous on both the left and the right side. Using this formula is pretty straightforward. So when you want to solve questions, all you need to do is just substitute the values accordingly to find the unknown value. But some of you might be wondering, why is V equal to F lambda? So let's just prove the wave equation here so that you understand how this formula works. This equation is actually derived from the speed formula. So now we know that speed is distance over time. So when it comes to the waves, you can think of, okay, distance is how far the wave has traveled, and of course the time is how much time it took for the wave to get there. Now we're going to take some of the wave features here, that means a measurable quantity of the wave, and substitute them inside this wave. So using a transverse wave as an example, let's say you want to take the distance of one wave. So distance of one wave is equivalent to wavelength, right? Because wavelength is the length of one wave. So instead of writing distance, I'm going to write wavelength because we're measuring it for one wave, which means that we need to take the time for one wave. Now, we already learned that the term for time for one wave is known as the period. So I'm going to write here, period. Now, I'm just going to use symbols here to make this easier for our substitution. That means lambda over t. Now, let's recall, we did learn that there is a relationship between frequency and period. So I'm going to write that on the side here in a different color. We know that frequency is 1 over period. So F equals 1 over t. If we come back to the formula at the bottom here, we can rewrite this as 1 over t times lambda. 1 over t is equal to F. So you'd get F lambda. And speed, as we know, is V, and that's how we get V equals to F lambda. So that's how this equation was derived. Now, some of you might be wondering, okay, that's all very well and good, but why don't we just use the speed formula? Yes, you can, but sometimes the values of the waves are expressed in terms of the measurable quantities that we've learned. That means we actually find the value of the wavelength, of the frequency. So rather than use distance and time, if we have the frequency and the wavelength of the wave, we can calculate the speed of the wave. So the values of the wavelength and frequency are kind of like the identities of the waves. So they're unique to the individual waves. And the next question could be, why don't we use period? Why do we have frequency? It's because when we talk about the values of the wave, it's easier to remember it in terms of frequency rather than period. For example, if we were to talk about a sound wave and you say, oh, the sound wave has a frequency of 10,000 hertz, it's much easier to understand because 10,000 hertz means 10,000 of those waves in 1 second. So we can remember it as, oh yes, there's a lot of it in 1 second, that's why it sounds like a very high pitch. But if you want to express it in period, it's harder for the brain to comprehend. For example, if you say, oh, the period of the wave is 0.00000001 second, then you'd be like, 0.00001. So you see, it's harder for most people to be able to make sense of that number, whereas frequency, much easier. That's why we prefer to use frequency when we talk about the values that are associated to that wave. So because of that, that's why the wave equation uses frequency rather than period. Now, if you'd like to find out more about how to use this formula, I'll prepare another video where we'll go through some examples on how to use this equation. In the meantime, this video has been already quite long, so let's bring this to an end. And I hope you found this video to be helpful and educational. Do subscribe to get notification on more free physics lessons, and of course check out my YouTube channel for videos on other topics which you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. If you'd like access to notes, quizzes, as well as syllabus updates, do check out my website at physicsrocks.com. Happy studying!